Hello and welcome again. So hope you are all doing very fine, and we continue our exploration of KiCad, an open source free electronic circuit and system design software. And we have covered a lot of earlier modules using KiCad and Spice inbuilt with it, and we have explored a variety of circuits. In that series, today we have brought to you another circuit of bridge amplifier. So this circuit can together be used to read a sensor output, mainly a resistive sensor output. For example, you must have heard about a strain gauge. A strain gauge is a sensor which experiences a change in strain when an external force is applied upon it, and in response to that it changes a material resistance of its own. So when there is an external force applied to the sensor, which is strain gauge, it shows that change, or it responds to that force as a change in its nominal resistance. And how to read that resistance change and convert it in equivalent voltage, that is the topic of today's discussion. So as you can see, we can model a sensor which is a strain gauge using this variable resistance here. So I have got four resistance, 1, 2, 3, and 4, that is arranged in a fashion that makes up a Wheatstone bridge, a popular Wheatstone bridge. At the junction right over here, I have an external voltage supply, like labeled as VEX, and that VEX is coming from this DC voltage source, which is set to be at 2.5 volt. And then the it is known that the nominal value of the strain gauge sensor is about 120 ohm, and it will experience a change in resistance from minimum value of 115 ohm to the maximum value of 220 ohm. That is according to, let's say, manufacturer specification or data sheet. And so nominal value of this strain gauge sensor is 120 ohm, and therefore I have chosen the other three values of the resistance to be the same, that is 120 ohm. This resistance is chosen to set the common mode voltage of the overall circuit. Based on that, your total swings for the inputs and outputs of the amplifier can be set. This is a two-stage, or using two Opamp, an instrumentation amplifier. So if you see the first one, you see there are positive and the negative pins. The positive pin is connected to the one end of this Wheatstone bridge, and the negative pin is receiving an external voltage of, which is called as a reference voltage of 2.5 volt. This is also set to set the input and output common mode voltage range so that the circuit behaves linearly for the entire input swing and output swing. There is this resistor of 20K. Now, from the output, we have negative feedback going to the negative pin of the input. Then output of the first stage is right over here. Then there is a resistance, and here we again have a negative feedback and going back to the negative pin of this. So these values of the resistors are as shown. So you see that there are two negative feedback in one configuration. And the second stage is receiving the input from this line going to the negative. So both these amplifiers are configured as an inverting amplification stage, and the positive pin of this is going to the junction of the Wheatstone bridge on the other end. So these 2 points are called as V1 and V2. And here the output of the amplifier is again going back to the negative pin. So that's the negative feedback. And similarly, this resistor together with this resistor, that feedback is also coming right over here. Now, how this circuit is going to work? So you have this 4 resistors bridge. When there is no change in the resistance of the sensor, which is right over here, the differential voltage, or you would say the voltage at this node and the voltage at this node, are approximately equal. Ideally, they are equal. And because of that, this voltage is going to the positive pin right over here. This voltage is going to the positive pin of this amplifier right here. So when, and accordingly the outputs are available. But when there is a change in resistance of the strain gauge sensor, because somebody applied an external force upon it, the bridge is unbalanced. It goes from initially balanced condition to the unbalanced mode now, creating a voltage difference or difference of the voltages at these two junctions, which are again going to the respective positive pins. So V1 and V2, or V1 minus V2, is applied here at the positive pins, and accordingly your output will also vary. So change in resistance is being converted into equivalent change in voltage, and change in resistance is happening due to input, that is a physical quantity of force. Okay, so this is the power supply pins, that is VDD and VSS. I am using plus minus 15 volt, and with respect to ground, I have explained in earlier models so many times what is the importance of PWR flag. This is just specific to the KiCad. Whenever we are doing the providing power to the circuit, we have to specify in the KiCad where the power is coming from. That's the convention in the KiCad. So if you are new, refer back to our earlier modules to understand it fully. So this is the two-stage amplifier, which is processing the signal coming, or differential signal coming from the Western bridge. So this is a typical bridge amplifier circuit used to process the strain gauge sensor output. So that's the complete electronic system. Now, the most important part is I have used a generic macro model or spice model for the Opamp here for U1 and U2. So what I have done here, I went to the library right over here and picked up the model from the library and placed the two Opamps right over here. Also, I have explained in our previous model how to do that. So if you are new, you go back to our previous models, you will find a wealth of information, including what I'm talking about now. So if I double click this, I see that I have got the data sheet, which is there inside the ngSpice source. The symbol pins of the first pin is positive pin, second pin is negative pin, 3 and 4 are VCC and VE, respectively 5 is output. I click here and I see that I've got these parameters of the generic Opamp. This you see here, the model is built in Opamp from the KiCad. So I haven't done anything specific. However, if you want to use the manufacturer provided IC for the Opamp to have a real world design of instrumentation amplifier to process signal from strain gauge sensor, you can do that by Googling a specific spice model for the Opamp IC, and then download the spice model into your computer and then call it right over in the file. Okay, we have covered numerous models, how to do that based on that in earlier models. So you are encouraged to go back and refer to those models right here. So now parameters, what are the parameters for this generic built-in Opamp? I have a pole frequency of 20 Hertz. I have a gain of open loop gain of 20,000. I have an offset voltage of 10 millivolt, and our output resistance of Opamp is 10 ohm. If I click the code, this is how the KiCad calls it in the simulation when it does the simulation. Now I click the pin assignment. You see that this information about the macro model, the generic model of Opamp is given. Pole is 20 Hertz, gain is 20,000, offset is 10 millivolt, resistance is 10 ohm, etc., etc. And you can scroll it. We have explained so many times in earlier cases. But the most important, the mapping between symbol pin and the model pin here. And I haven't done specifically anything right here, but when I use the manufacturer provided model, I will need to ensure, and I will have to do few adjustment here so that my symbol pins will be mapped exactly to the model pins as shown. So here I haven't done anything because this is generic model. Okay, I click here and then I click here. Same goes with this. I have shown here, so same applies to this. Once that is done, what I can do, I can go for ERC. Just I want to ensure that my schematic is correct. So I have performed that earlier. And with that, I saw 0 errors and these warnings are coming, but I can safely ignore. That will not affect my performance of the circuit. After doing that, what I am interested in is simulation. I want to see the output variation in response to the change in resistance of the strain gauge. And that change in resistance is, we understand, is happening when strain gauge experiences an external force upon it. So let us do that. So what I'll do is I will click open the simulator. Once the simulator is opened, you can see right here, I have to choose the new analysis tab. Once I do that, I've got to choose the analysis. So I will go for DC sweep analysis. Now, what kind of source I want to sweep? Voltage, current, or resistance? Since I have included a variable resistance in the circuit, that's why KiCad is showing me this option to even sweep the resistance. Okay, and now what resistance I can sweep? I have so many resistance, but only one of them is a variable. So R12, not any other I want to sweep, but I can sweep them as well, but R12 is what I want to sweep. So I go here and I say sweep type is R and then sweep R12. Now starting value, I know that nominal value is 120 ohms, so why not 100? Final value is, let's say, why not 200, and increment, let's say 1 ohm, a very fine steps I want to do. And then compatibility mode, whatever you can do, let's say, okay. Once that is done, I need to click this run simulation button. Once that is done, simulation is performed at room temperature. Now look, what am I wearing here? In fact, I am wearing the resistance. So let me find that out. There is a power, current, and all voltage is showing. Okay. So with that, here V of VO2 is what I'm interested to plot. You can see that. Why? Because if you look and check into the schematic, VO2 is my final output. So we'll see now in response to change in resistance how the output will vary. So come back here. And with the simulation done, let us click here and look at this. And we now want to interpret this result, which is easier. So you see now, when I don't have when my resistance is 100 ohm, my output voltage is minus 6.4 volt. And when there is an increment of resistance from 100 ohm up to 102, let me just fit on the screen. So you see from, so I have got offset voltage right here, right? So, and then when I go up to 150 ohm, I have a linear variation of the output. So output is linear when resistance varies from, let's say, 100 to 150 ohm. That's it. Okay, but after that, what happens is that output is saturated to the positive supply rail of 15 volt if I have a change in resistance beyond 150 ohm. So what I'll do, I will zoom in this portion and look at this is the linear range of my output. Okay, so -5, it starts with that, and I have up to 150 ohms. So that's my linear sensing solution of the strain gauge. My bridge amplifier is behaving that. But this is all happening because I have used like the kind of generic Opamp model. So what about we'll play around with it? Let's say I want to play with the parameters. So simulation model, instead of gain is 20K, let us play with, let's say the gain is about, let's say only 1000, and we'll see what kind of things will change in our circuit. So with that said, go back to simulation and now look at this. Click simulation here. Is there any specific change? Not much, maybe a little bit, but you see now the output at 100 ohm is about minus 4 point something, minus 4 volt. Earlier it was minus 6, right? So that is a change here. So it's about minus 3.5, something like that. Okay, so those are the things. You can see that the offset is coming right here. Now, again, in fact, you have to change the op-amp conditions for both also, or one op-amp only. Again, go to simulation. Let us say you have the 1000 ohm. Instead of that, you keep it 20, but instead of 10 milli, just say 100 micron. Offset is 100 micron, and we'll see what changes it can bring here. Okay, so with that, go back, click the simulation, and look at this now. Offset, effect of offset voltage on the linearity of your output. Your output linearity is increased. Your output is saturated to minus 15, but thereafter, let's say you have a large range of resistance. So you start with 100, approximately 100 ohm right here, fit on the screen. And from 100 ohm, you have like extended your linear output range up to 175 right over here, 178 ohm. So you see now, these are all parameters that you can play around. You just change many things one by one on your op-amp, or some other parameters. For example, this voltage, power supply voltage. Let's say I want to use like, let's say 5 volt here and minus 5 volt here. So obviously I will have 5 each. And then if I go back and simulate, look at this now. The linear range is now between these 124 ohm to 150 ohm. You got the smaller really linear range. So things will change like this, right? So maximum supply voltage is helping you to get the wider linear range. So this is how the strain gauge sensor, bridge amplifier for the strain gauge sensor will work. Exercise for you is to replace these op-amps with the manufacturer provided SPICE model and evaluate the performance, and put in the comment section box what kind of op-amp will be most effective for such applications. So if you'd like this, click the like, share it with others for a wider reach, and stay tuned for more engaging content like this. Till then, wish you a very happy learning.